Hi everyone, I've been asked to work through a couple of videos talking about limits and discontinuity and also where graphs are differentiable and not differentiable. So this first question is asking us to give the values of x at which discontinuity occurs. So here's my graph shown. I've got a few different parts here. It's changing a lot. And what you need to remember is that a graph is discontinuous, or this is a discontinuous when, actually, let's write that a different way. I'm going to say the graph is continuous if I can draw it without lifting my pen. Continuous if I can draw it without lifting my pen. So let's look at this graph and think, well, where can I draw it without lifting my pen? So start on the left-hand side. I can cruise along over the top here, and I don't need to lift my pen to go through these points. But at this point, there's a hole in the graph. So I've got to stop. I've just lifted my pen off the paper to create that hole, and I put my pen back down to draw that part. And then the last bit, I've obviously got to lift my pen again to continue my graph in a completely different spot. So I've created these spaces where the graph had these key features, and I had to lift my pen at that point, so that's a point of discontinuity. I had to lift my pen to create a hole here, so that's another point of discontinuity. This point over here though, on the left where x equals 1, I was able to move through that. Because the graph existed at that point, I could move through that graph without lifting my pen. So that part is okay, that part is continuous. So let's write down those first. It's discontinuous. If I could spell discontinuous right, that would be better. Discontinuous at x equals 3 and x equals 4. So let's now explain why. So the one at x equals 4, that's much easier to explain in my mind. So x equals 4, really simply, we can see that the graph has a jump from one point to the other. So when x equals 4, the graph's defined and it exists here. Now let me draw a nice little arrow for where I'm talking about. It exists right there. Okay, so at the value x equals 4, there's a point on the graph that exists. I can draw that point, I can calculate that y value if I have an equation, and we're all good. So it exists in that sense. But it also, on the left-hand side here, it's heading towards a different value. And this is where the limits come in. So what I say is the limit as I approach 4, so as x approaches 4 from the left-hand side or from the negative side, it's approaching this value, let's say about 3. So the limit as x approaches 4 of f of x is, we're going to say 3. But if I approach that point of x equals 4 from the right-hand side, so the limit as I come from the right-hand side, it's approaching this value all the way up here, which I'm going to say is roughly 6. So the limit from the left-hand side, and the limit from the right-hand side, they don't match. So when those limits don't match, basically when the point that we approach from the left is different to the point that we approach from the right, then we have a point of discontinuity. So limits don't match. So point of discontinuity. All right, at x equals 3, so let's look at that one. At x equals 3, this is really straightforward, and it's sort of a bit harder with going into limits. I don't want to go into all of that stuff right now. So I'm just going to say at this point x equals 3, the function doesn't exist. There's a hole in the graph. So if there's a hole in the graph, it can't be continuous at that point because we've got a value before it, we've got a value after it, but we've got at that point right there, no value exists. If I was asked to calculate the value for y when x equals 3, I can't do it because a function doesn't exist. So if the function doesn't exist, then it's discontinuous. Therefore, discontinuous. Now I will talk about this point where x equals 1 just briefly. So at this point, it is continuous. All right, so my graph is continuous because the limit from the left-hand side is equal to 2. And the limit from the right-hand side is also equal to 2. So a value that we approach from the left is the same as the value that we approach from the right. And because it's a closed-in circle, the graph exists, the function exists. So therefore, it's continuous. But that's really interesting because I have what I've referred to in class as a pointy point. If I zoomed in on that point and I got closer and I got closer and I got closer, we wouldn't approach a straight line. We would be approaching a point. So as I zoomed in, I'm going to get this exaggerated point, not a smooth straight line. So it won't be smooth. If it won't be smooth when I zoom right in, then it's not differentiable. So it is continuous, but not differentiable. Okay, the derivative does not exist at that point. Okay, that was the first question. Let's have a look at the second question. So the rule of a particular function is given below. For what values of x is the graph of this function discontinuous? So again, we're looking at discontinuous. We've got to find out whether the limit's the same from the left and the right-hand side, and if there's any holes or gaps in this problem. So let's actually start by quickly drawing a graph of each of these parts. So this is my piecewise function, or a hybrid function. And all it's telling me is that I've got 3 different parts for 3 different sets of x values. Okay, so when x is less than 1, the graph is equal to 2. So let's quickly crank axes on here. Now I haven't drawn these graphs before, so hopefully I don't make too much of a mess of it. When x is less than 1, my graph is equal to 2. Here we go. I'm going to call that 1. And I have to have an open circle here because it doesn't exist on that line. Right, second part of the graph. Let's draw x minus 4 squared plus 9. Sorry, minus 9. Don't know why I said plus there. X minus 4. So x minus 4 squared moves it to the right 4 places. 1, 2, 3, 4. That's going to be my turning point. And then I've got to go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Might as well use my grid lines. Here's my turning point. And it is a parabola. So it's going to go through there, there, there. Here is my parabola. Something like that. Except we only want to have this graph from 1 to 7. So 1, 2, 3, 4, 5, 6, 7. I actually only want to have this graph from there to there. And they'll be the axis-intercepts. Now you can go work through, calculate the axis-intercepts if you're not sure where it is. And I know it's equal to 1. And then again, at this end, I need to have an open circle. Don't include that value of 7. So straight away, I know I've got a point of discontinuity at x equals 1. All right, let's have a look at x minus 7. Do I have a graph here if I draw a graph of x minus 7? So x minus 7, it goes through at negative 7. That was negative 9. So let's just put this on there for negative 9. 1, 0, and 7, 0. Cool. And my graph has a gradient of 1, so it's going to go up 1, across 1, 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 so on and so forth. So that will be my graph right there. Except I only want to have this graph of x minus 7 when x is greater than or equal to 7. So I start at there. I'm going to colour in that point now because my graph exists at 7. And then it's going to be this line here on forever. So what ended up happening with this point here? Now, for the parabola part, so the parabola approaches 0 when x equals 7, and then the linear graph approaches 0 when x equals 7, and the function exists at x equals 7. So therefore, although we've sort of got this point where the gradient's going to change at those 2 points, it is continuous at these points. Let's change my pen. So discontinuous here. Whoops. Struggling to spell today. Discontinuous here at x equals 1, and it is continuous at x equals 7. But again, if I zoomed in on this point, it wouldn't approach a straight line. So the gradient doesn't exist at x equals 7, but it is continuous at that point. All right, that's the end of this question. That's the end of the